All right, guys, so hey, I wanted to go through this lab. I know we went through the first section before, so I'm just going to kind of breeze through that. Um, and I want to go through the rest of the lab that we were supposed to finish up last week. So what you guys were looking at was electric potential. And the first part was just graphing electric potential and seeing what it looks like. So if we have a positive charge and a negative charge, you're able to look at the electric potential. Basically, it's zero potential in between, and then you're able to plot, negative 10, negative 20, negative 30, positive 10, positive 20, positive 30. And that should produce evidence that equal potential is an inverse relationship, whereas the closer I get, the bigger it is. And that's going to prove our equation, which is V equals KQ over R. Are equal potential lines evenly spaced? No, they are not. As they get closer, they actually get closer together as we get closer to our charge. As we get further apart, they actually spread out substantially more. Here's kind of the difference of distance listed right here. Okay, so again, we're proving this equation, V equals KQ over R, and that it is this inverse relationship. Second thing is we're looking at parallel plates. So we have positive charges on the right, negative charges on the left. We have an electric field then pointing from right to left, and that's a constant electric field. And then if we were plotting the equal potential lines, we have what we see here. We're 0 volts in the middle, and then as we move to the right, we're going to become more of a positive potential, 10, 20, 30, 40, and so on. And then a negative potential, negative 10, negative 20, negative 40, and so on. So that's what the electric field and the electric potentials should look like. So all the fields points from towards the negative, equal potential lines. And the big thing is that they are perpendicular. So the electric field and the equal potential lines are perpendicular to each other. So they should always be perpendicular. And they might not be drawn perfectly here, but they should be perpendicular to each other at all places. Two positively charged particles A and B are placed as shown. Particle B has 3 times the charge and 5 times the mass. Compare the motions. So both of them are going to move straight across towards the negative plate. However, I said that B, the force on B is larger than A. You can't use this equation necessarily. You have to use E equals F over Q. However, I said A has a greater acceleration. Basically, acceleration is force over mass, and versus 3 force over 5 mass. So that's kind of how you can compare their forces and their accelerations. Part D then says find their final velocities. And so this is where we start using that equal potential idea, where basically they are both starting from a high potential, and they're going to move this direction towards a low potential. So in this case, they have high potential energy, and they're going to move towards a lower potential energy, which means they're going to gain kinetic energy. So their energy is being converted from potential energy at this location to kinetic energy at this location, and I'm going to find the velocity. So to do that, I'm going to use my equation, which is change in energy, which in this case would be either a loss of potential, a gain of kinetic, or the work done by the electric field is charge times the potential difference. My charge is 1.6 times 10 to the negative 19. My potential difference for me, everyone's is going to be a little different, but I said they started at 40 volts and they end at negative 70 volts. So final is negative 70 minus initial, which is 40. So my change in potential is 110 volts. Multiply that by my Q, and that's my change in energy. So this is my change in energy. My kinetic energy then is that same value. Because they started with 0 kinetic energy, their final kinetic energy is going to equal their change in energy. That's what this is. And so then I set that equal to 1/2 mv squared, and I solve for V, which is 2 times my kinetic energy, which is my change in energy, divided by my mass, and I get 2.65 times 10 to the 6th. Same thing over here, same process. Again, different charge, different mass, so a little bit different numbers. I get 2.1 or 2.06 times 10 to the 6th. Everyone's could be a little different depending upon what your voltages were and what voltage you said they started at. No big deal if you're a little bit different, but they should be somewhat close to what we're getting here. The next part has 2 point charges. We can tell that the charges are different size based on their potentials, and we can see that this charge is actually a bigger charge than this one because their equal potentials are more spread apart. So I drew my electric field lines, and I can draw my electric field lines. Basically, I have to make sure that my field lines are always perpendicular to my electric potential. So these are positive potentials, so I know that these are positive charges. So I'm going to draw my field pointing away. and my field lines are always perpendicular to the equal potentials. It then says, describe what the electric field lines represent. I said the direction the electric force would act on a positive charge. Label a position where an electron would have a maximum potential energy and a proton. So I said an electron would have the maximum potential energy out here because it wants to come closer to these positives. So the most potential would be furthest away from where it wants to go. A proton, I would say, would here. It's furthest away from where it wants to go. Because it wants to be next to these, far away from these positives, the most potential energy would be right next to them. Predicted path of a proton, right here. I'd say it's basically something that looks like this, right? It's going to be repelled from this, and then it's going to be repelled from this, so it's going to take some path that looks like that. Now, it doesn't have to be very specific, but just maybe general, that might be what it looks like. Now it says calculate the maximum velocity and kinetic energy of the proton, assuming it started from rest. So here's what we know. It's going to start right here. That's 40, 50, 60, 70 volts of electric potential where it starts. As it goes away, we see that the voltage is going down, and eventually, if there's no negative charges, it's going to get to a voltage of 0. So I'm going from 70 volts to 0 volts. That's what I'm using in this problem. So my change in energy is Q delta V. My change in voltage is final minus initial, 70, or 0 minus 70. So my change in potential is 70 volts. So applying that here, I have my charge of a proton times my change in potential, and this is my change in energy. That change of energy could be 1, a loss of potential, 2, a gain of kinetic, or 3, the work done by the electric field. Okay, it wants to solve for velocity, so I'm going to say that is the change in kinetic. So because my initial was 0, that's my final kinetic energy, and then I'm again solve for velocity using 1/2 mv squared, and I get a value of 1.16 times 10 to the 5th. Again, should be close to that because these values are pretty well known. Oopsie, there we go. Explain why you wouldn't be able to do it for an electron. Well, the electron wouldn't move away. It would, if it started here, it would be attracted and it might move all around. So what I said was you don't know where the electron would end to find the final voltage. It would move around the electric field continuously, either speeding up or slowing down based on the attractive or repelling forces of the charges, and so we wouldn't really know where it ends, so we couldn't do this because we don't know a change in voltage. Last one is a scholarship. That's my best guess based on the simulation, right? There's going to be some point between the positive and the negative where we have 0 potential. It's going to be closer to the positives than it is the negatives based on the negatives having more charge built up at each location. All right, so hopefully that's a good overview. I know it's quick, but I think it's useful to see kind of how I work through it as well as understanding how we're applying the math to these situations.